The next section of the book has to do with the atmospheric system. Now, the atmospheric system is separated from the terrestrial ecosystems. But as we said, it's a state factor. It generates state factors such as climate, and it's an important component of understanding how terrestrial ecosystems function, because there's a lot of interaction between the atmospheric system as well as the terrestrial ecosystems that we would like to study. In this first part, we're going to think about the chemical composition of the atmosphere, and the authors state that the chemical composition of the atmosphere determines its roles in Earth's energy budget. Now, the atmosphere itself is composed primarily of a few chemical constituents. And this is something that everybody, I'm sure, would have covered to a certain degree, but it's good to cover it again. So the major gases in the atmosphere, we have nitrogen gas is N2, and that's about 78% of the atmosphere. And then there's also oxygen, which is roughly 21%. Argon is there too, about 1%. And then we get into carbon dioxide, which is somewhere on the order of 0.4%. Now, when we think about gases in the atmosphere, it's really important to think about not only the activity of those gases, but how long those gases reside in the atmosphere. And for that, we do calculations of mean residence time or turnover rate. And I'm going to go through the differences between mean residence times and turnover rates of gases in the atmosphere and what they are for the different major constituents. So in general, when we've been talking about ecosystems, we generally take a pool-flux approach. So there's fluxes into a pool and there's fluxes out of the pool. And if a pool is at steady state, meaning that the fluxes going into that pool are balanced by the fluxes going out of the pool, so they're relatively equivalent, we can start to do calculations based on the size of the fluxes in or out and the pool size. Now, when we calculate the mean residence time, which is essentially how long an average molecule is going to reside in a pool, essentially it's the mass of that pool divided by its flux. So if you know the mass of a pool and you know the flux into the pool and you assume that that pool is at steady state, then you can calculate the mean residence time. Now, the turnover rate is simply the reciprocal of the mean residence time, and instead of being mass over flux, it's flux over mass. In each of these, it's the same information in mean residence time or turnover rate. There's different ways of expressing the same general idea, and we're going to just go through and take a look at mean residence times and turnover rates for each of those major constituents of the atmosphere. For nitrogen gas in the atmosphere, nitrogen gas is a relatively large pool. There's a lot of N2 in that atmosphere. 78% of the atmosphere is made of N2. And the fluxes out of that pool each year are relatively small. This isn't shown to scale, just only to show you that the fluxes are relatively small coming out and going in. And fluxes out of that pool are generally biological, so nitrogen fixation by plants that we'll talk about, or lightning fixing N2 into nitrous oxides, for example. And then the fluxes going back into the pool are also relatively small and pretty much balanced by the fluxes going out of the pool. When we do the calculation about what the mean residence time is of N2 in the atmosphere, it's relatively long, 13 million years. And that turnover time is 0.0000077%. So very little is turning over, and N2 is staying in the atmosphere a long time. In contrast, oxygen is a little bit more balanced. So relatively larger fluxes in and out of the oxygen pool and a smaller pool itself. And the mean residence time of oxygen in the atmosphere is only 10,000 years, somewhere on that order. And that gives it a turnover time of 0.01% per year, which means that 0.01% of that oxygen pool is removed from the atmosphere or replenished from the atmosphere every year. In contrast, CO2 has a much smaller pool and much larger fluxes, and as a consequence, the mean residence time of CO2 in the atmosphere is actually only 5 years, and that's a turnover rate of 20% per year. So CO2, much higher, much lower mean residence time. It turns over a lot faster compared to N2 or O2. And as you read through the book, you'll see also that it's important to think about that the reactivity of these gases in the atmosphere, and this extends beyond CO2, is not necessarily proportional to its radiative importance. So some of these gases turn over faster than others, and some of them are a lot more important as far as the radiative balance of the Earth is concerned. So the authors have a statement that some of the most important radiatively active gases such as CO2, nitrous oxide, which is N2O, methane, which is CH4, and CFCs react relatively slowly in the atmosphere and have mean residence times of years to decades. And so when we think about the global warming potential or the warming potential of these gases, we can't just think about how much energy or heat they absorbed, how much long-wave radiation they absorb, but we also have to think about how long they stay in the atmosphere, because some of the gases that get released might not necessarily have more importance as far as absorbing radiation in any given unit of time, but they can have a long mean residence time and have a long impact. And so in general, understanding the atmospheric system requires understanding which gases are there. But we also have to understand how long they stay there, because it's not just what their activity is per unit time, but how long we expect them to be there. How long they're in the atmosphere really depends on how well we can make calculations, not only of the quantity in the atmosphere, the concentrations, but also their mean residence time or their turnover rate.